Good afternoon, dear viewers. Thank you for your interest in the Robocom project. My name is Egons Lavendelis. I'm Associate Professor at Riga Technical University, Riga, Latvia, and I was a principal investigator on the Latvian team. And I would like to tell you about our main results of the project achieved here in Riga. And that means I'll speak about long-term adaptivity in multirobot systems and Vayabots model that we have developed. So what is the current problem that we are addressing? It's the fact that design of robotic systems and especially multi-robot systems is becoming increasingly complex because such systems cannot foresee all possible states that the system will be. Consequently, the system has to adapt to internal and external changes, which means changes in the tasks the system is doing, changes in the system itself, and changes in the environment where the system is. Moreover, we need it to do it in long term. So we need long-term adaptivity or viability, as we will be calling it in our research. Is it possible? Well, yes, many types of systems are capable to do so, starting from human bodies and other natural systems, and ending with artificial systems like long-term, companies that have been here for more than 100 years, like IBM Corporation, the Coca-Cola Company, and many other systems that have been capable to adapt to many changes over the years. So we wanted to ask ourselves, is it possible in multi-robot systems? For now, it has not been achieved, but we would like to check if existing models for long-term adaptivity from organization theory can be applied also to multi-robot systems. And in particular, we took one model that, according to our literature review, was the most promising, named Viable Systems model, and tried to apply it to technical systems, in particular multi-robot systems. So we started with model development, which was our stage one. As a result, we developed a Viabots model. The name comes from viable and robots, Viabots put together, and it came out from adaptive systems and organization theory research. In stage two, we validated it in simulated environments, so we developed a simple simulator. And stage three, we applied to two physical multi-robot systems. One of them is shown in this slide. So what is this viable systems model? First of all, it is the model that focuses on organizations and not robotic systems. On the other hand, it's validated on both companies and also many other use cases like structuring Chile economics. So the bottom line, it is working in an organization. So what it is, it says that the organization to be viable needs to have 5 types of functions or 5 subsystems. The first of them is operation, the actual workers doing actual work. You need the local control for them or local management. This is system number 2, which organizes the work of a team, like in case of a university, it's a research lab or lecturing department or any other structural unit. When you cannot solve the matters inside your department, you need a global control in your organization. This is a necessity, but in many cases it's not enough because you also need to understand what's happening around your organization, where you need to go. So you need intelligence that predicts what's happening, and also strategic development, where you are heading. So the policy, which is system number 5. So we took this model, and what we did with it, on one hand, we have robotic systems, autonomous robots. On the other hand, we have this model, the viable systems model. The model defines which functions are necessary for the system to be viable. On the other hand, the robotic systems define what resources, what machines are existing in the system. So for each such machine, we defined an intelligent agent, which formed a multi-agent system. And this multi-agent system is an abstraction layer for the management of such a multi-robot system. And each of these agents is taking these roles dynamically. So we have to define that one particular agent is taking intelligence role, at least one is taking global control, And also for each operations that we need to do physically, where we need our particular workers, we also need an agent that is doing this. And such an abstraction allows us to reorganize who is doing what particular moment to make the system capable to adapt to changes in long term. So what we did with such a system, we created two multi-robot systems. The first one was the conveyor belt based production line, where we started with simulated environment, where the conveyor belt was simulated and it delivered 3 types of parts, and each of them must be processed by one worker. And so the system was these workers, the multi-robot system, where each robot was a worker doing a particular job with particular part. So the goal of the system was to process incoming parts fluently, to keep the conveyor running, because if you cannot process the part that is coming, you have to wait for the robots that can do that. So how did we implement the particular model? You might notice here that we have here only 4 of the systems of viable systems model. That's on purpose, because the system number 5 policy was left for humans to define the high-level goals of the system. So the system is not deciding what it will be doing in long term. The main goal is given by the human, and then these 4 subsystems are organizing the system to achieve this goal. So these 4 ones are operation, local management, control, and intelligence according to viable systems model. And let's look at the bottom level, which is detailed on the right side of the screen at the moment. And these are the workers that are capable to do one particular thing. This is S1, and it has multiple units. And then for each type of work, we have the corresponding S2 unit, which is managing the S1, the S1s. And what these S2 units are doing, they are calculating how much workforce they need to successfully process all the tasks that they will be given. And if they see that it's not enough, they ask other ones by sending a CFP message to other S2 coordinator to get one more worker. If this guy says, okay, I have more than enough, or I have better situations than my colleague, I can give one worker away. Of course, such simple mechanism not always will lead to an optimal distribution. That's why we need the control that knows all these numbers, how much workers are dedicated to each job, and it can be distributed based on those numbers at S3 level when we see that S2 fails. Moreover, we have to know what's happening in the system, what's coming next. Maybe we don't need to change the tools to assign the worker to another department. And that's why we need forecasting or statistics, which is system S4, or in this picture on the top of it. So that was the model in very brief, yeah. And what we did based on that, we first implemented a simulated environment. Here you can see all the workers, what they are doing. So Viabot 1 till Viabot 8 in this example. And for each of them, you can see what part they're processing, what are the capabilities of this robot, and the current status. For example, it's charging or doing particular task, or is waiting for a task, or is idle. Then you can see the log where we have finished parts, the upcoming parts, and the resulting values. So how many parts were processed, how much time it took, how much time we were waiting, and how much we have workforce dedicated for each of the parts. So this allowed us to quickly simulate many different scenarios, and the results of the experiments were the following. We divided our experiments into parts. So within these stages or parts, we changed the part distribution. These are percentage, so 40% A, 30% task B, and 30% task C. Here the distribution is completely different, as you can see, different, different, and different. So we kept the environment changing to see how the system adapts. And we did 4 experiments, or 4 types of experiments, and these lines are average values. So in blue line, all the model is active. Then we turn off the intelligence. Then we turn off the local coordination, and then we turn off then we talk of global coordination and local coordination. As you can see, that if we don't have any organization at all compared to the full model, we have twice more efficient system in terms of how much time that conveyors is stopped, because we can have no workers that is capable to process. Also, if we compare it to policy, it is to the system without intelligence, then we already also have approximately 10% improvements. Based on these encouraging results, we created a physical conveyor-based system where we again took conveyor system with part mounting task, and it was simulated with just putting cones into boxes because we didn't want to pay a lot of attention to hard part mounting tasks, so it was a simple one. We had heterogeneous robots, Baxter, ABB manipulator, and simple custom-made 3 degree of freedom manipulators. You can see that the system is highly heterogeneous in terms of available machines, available resources, and speed of action that they can do, even in such a simple task as putting cones into the boxes. So how did we implement the system? We implemented this multi-agent based abstraction layer, which is connecting everything together, starting from user's computer, conveyors controller, and particular manipulators, and each of these are controlled by a particular agent. So an agent controls a manipulator, an agent controls the conveyor, and these agents are communicating to each other, and as a result, they are creating an optimal distribution of agents. So how does it look like in the video? So here you can see the ABB manipulator, the Baxter manipulator, and the boxes are coming over the conveyor belt, and according to the plan, these robots are putting in the parts into necessary places. The plan is to fill in the box with the corresponding. So what experiments were done based on that? We changed the patterns, and we changed the order of those patterns to see how the robots can adapt. For example, in the first experiment, we have 1 box like that, 1 box like that. In the second one, we had boxes like that, and these A and Bs were put in different orders. And again, we experimented with fully active model and part of it off, intelligent functions off first, and then intelligent and control off. So what were the results? The results were the following. In all 4 cases, as you can see, the static distribution, so without the model, was the worst one. If we have the full viable systems model, then the results were the best. The blue one is the blue average processing time for each part is the lowest, as you can see. If we compare just on average of all of our experiments, full viable systems model or no model at all, then the difference is a bit more than 14%. So this proved that such a model can increase the efficiency of production line significantly. Another experiment was done with mobile multi-robot system. The task is to explore the environment. The platform is iRobot Roomba, which are localizing based on distance measurements between robots, radio-based. So we need 3 beacons at every time, and other robots can be exploring the environment, and the role of the model is to reallocate tasks between robots. So you can see these robots. There are 5 identical robots with absolutely identical software, and they are allocating those roles from the viable systems model to each other. So first, 3 of them are becoming beacons. These circled ones, they take positions, and then others can localize themselves based on these 3 robots and explore the environment as necessary. Of course, the localization errors are quite high. Also, the robots might break down, but still the system was able to reorganize itself according to these errors, based on the model. So what was the result? We had 3 robots as beacons and others traveling around, exploring the environment, achieving the goals. And when the area was explored, those 3 moved forward. What did we prove with this experiment? We proved that the system can allocate the tasks as necessary using this adaptive method, this autonomous method. So to sum up, as you saw, we developed an organization theory-based model for the multi-robot systems. It is general one for used also for 2 different scenarios, and we validated it on 2 systems. First of all, on this conveyor belt-based production line, where the production was increased by 10 to 14%, and also we tested it in mobile robots. So we developed a model, validated it, and the results are promising. Why do we find it important? Because multi-robot systems are becoming more and more complex. Designing tasks is becoming very hard because we cannot predict all the situations, and that means we need such models to implement adaptivity in autonomous systems. And we think that autonomous adaptive systems is the future of robotics. That means we need general models to implement such adaptivity. So thank you very much for attention and interest in Robocom++ project, and thank you to the project which allowed us to do this research. And thank you for attention. Bye-bye.